and the flow in the backward direction. So there will be moments, there will be flow rates at which you have lower pressure drop in one direction than in the other. For Newtonian fluid, this is for Newtonian, the flow in the backward and forward directions is essentially the same. It's difficult to see in the pictures, but they're essentially the same. And as a consequence of that, if you, for instance, take the velocity profile along the axis at very low Reynolds number, it doesn't matter in the forward or the backward direction, the two profiles collapse. At a higher Reynolds number, they don't collapse. There is a phase lag, let's say, but the magnitudes are the same. As a consequence, the pressure drop for the same flow rate in the forward and backward direction is the same. The three sets are for three different aspect ratios, but they contain backward and forward flow. So the same pressure drop and as a function of flow rate, meaning no rectification, no fluidic rectification effect. Now, if you put a viscoelastic fluid, what you will see is that there will be instabilities, and they start. So at a given Weissenberg number, you may have instabilities in the forward direction, but not in the backward direction. Okay. From the pictures you have, it's not so easy to see. There's a lot of these bright spots are particles, sitting particles that suddenly stuck to the wall and give you a lot of glare, and so. In fact, the experiments, you have to throw away the chips after 10, 20 minutes because of the particles sticking at the walls, and you have to put new channels and repeat the experiments. So these become very hard to do. But you can see here the profiles along the same center line. If you compare the solid symbols, forward and backward, so you can see that the profiles are now quite different in magnitude. And at a higher Reynolds and Weissenberg number, especially at the higher Weissenberg number, because the Reynolds is low, the open symbols. So again, they are different. Pressure drop as a function of flow rate, you can see that in the forward direction, you have a higher pressure drop than in the backward direction. At very low flow rates, the pressure drop is the same. As at very high flow rates, you also tend to have more or less the same pressure drop. In fact, you can compute what is called the diodicity, which is the ratio between the forward pressure drop over the backward pressure drop at the same flow rate. And you can see is that there is a window of operation where there is a diode effect, a rectifier effect. Below, so at low flow rates, you don't find that, or at low Weissenberg numbers, you don't find that, and the high Weissenberg numbers, you don't find that. The three different curves are for different aspect ratios. So this, the viscoelastic instabilities can be used to create valves. If you put more and more contractions, you can almost eliminate the flow for the same pressure difference. So you can have a valve without any moving part by just operating and with viscoelastic instabilities. My last flow is the 4-to-1 planar contraction. This is a benchmark in computational rheology, so a CFT for viscoelastic fluids at 0 Reynolds number. We call it computational rheology. Initially, the computations for a long time, flows like flow around a cylinder, which is another benchmark, flow in a sudden contraction, they were very difficult. And usually, you could not achieve convergence above a certain Weissenberg number. For instance, this is data from the prehistory of computational rheology, meaning by that, before the beginning, before people start to use lock confirmation technique or other techniques to overcome the high Weissenberg number problem. And you can see the spread in the data, first of all. Even for Newtonian, there was some discrepancy. Anyway, we are measuring the flow is from left to right. There is a recirculation at the expansion plane, and we are measuring this length of the recirculation length, which is plotted as a function of Weissenberg number. So initially, the computations for a long time could not converge for Weissenberg numbers above about 2.5. Okay, they would all blow up. It was only with the advent of the lock confirmation technique and other techniques in the about 8 years ago that people started to be able to compute high Weissenberg numbers. Anyway, what happens is you have initially this recirculation here, and then as you increase the Weissenberg number, you start to have a small separation there. This is for the UCM model, the Maxwell model, or the Oldroyd B. It's more or less the same thing. The Oldroyd B is a Maxwell with a solvent. And then as this lip vortex grows, this corner vortex decreases. And what happens afterwards is that the lip vortex overcomes the corner vortex, they merge, and then the merged vortex, a single vortex, will start to grow with the Weissenberg number. We found that most of these flows are unstable. They are time-dependent. This is all published in this GFM paper. Various regimes, you can see some pictures, some snapshots. The flow is time-dependent, okay? There are small oscillations initially, and then as we increase the Weissenberg number, you see more and more strange features, and the flow is always varying in time and with a wider range of frequencies, okay? For instance, in the so-called vortex backshedding regime, this is a small movie made from the computations. The computations are 2D, and here you have the evolution of the length of the recirculation with the Debord number or the Weissenberg number, and these overbars are the amplitudes in the oscillation of XR. So as you can see, we start to have time-dependent flow at a Debord number of about 2, 2.5, and then they always keep increasing. So the various regimes that we had identified, these computations are 2D computations. They take a long time because we have to use very small time steps and also let the flow evolve for various relaxation times before we take the results, before we take the statistics. It's like doing DNS in turbulent flow, okay? We also computed the so-called quet correction as a function of the Weissenberg number. And here is the graph I showed you earlier. With the phase diagram at various, so as a function of the Reynolds and Weissenberg, in this case as a function of the elasticity, Weissenberg number, and then these are lines of constant elasticity. The elasticity number is interesting for experimental work because in experimental work you usually pick up a fluid, and the elasticity number depends on the fluid properties and on the size. So if you pick up a size, a given geometry and a given fluid, the elasticity number is going to be constant, regardless of the velocity, okay? Right, and with that, I come to the conclusions. So I've shown you that microfluidics allows you to do computation, to get flows at very high Weissenberg or Debord numbers and low Reynolds numbers. And when you have that, you really find various instabilities, viscoelastic instabilities. To compute them, you need some special techniques to overcome the so-called high Weissenberg number problem. The problem is associated with the nonlinear terms that I showed you in the beginning, where near geometric singularities or in stress boundary layers, the stresses tend to grow exponentially. So you need some methods to follow well this growth of the stresses in these regions. Otherwise, you may get aphysical values and the codes blow up. We are currently studying experimentally some of these flows, like the cross slot, and also getting into experiments with electroosmosis, the kinds of materials like surfactants. And of course, you can also explore a combination of viscoelastic fluids with surface patterning, magnetic fields, whatever you want. And I'm sure you will find always very interesting results. And finally, I would like to acknowledge the funding and, of course, some of our colleagues that have collaborated with us over time. Thank you very much for your attention.
Before I open the floor to questions, can I just encourage you to stay behind after this talk session is finished, because Roberta has some important announcements to make about food tonight, which you'll all be interested in. Having said that, are there any questions from the floor to Fernando?
When you do this splitting experiments and they go more to the left and more to the right, what kind of conditions are there to ensure? Are there outflow conditions to send them?
So what I showed you was computations. Okay, the outlet conditions are just zero gradient of the velocity, and you extrapolate linearly the pressure. Don't impose flow rate. If you do experiments, and we are starting experiments,